All right, so to start off with, we're going to talk about independent events. So if two things are independent, if you are independent, what does that mean if you are an independent person? You don't depend on someone. What did you say, Geronimo? You don't need help from anyone. You're kind of on your own, right? You're independent. Okay, so independent events are two or more events that do not change each other's outcome. There shouldn't be a period here. I don't know why there is. Okay, two or more events that do not change each other's outcome. Let's go. There's a pencil right by your foot. Okay, they're on their own. All right, so for example, if I roll a dice and I flip a coin, does my dice change the coin?
No.
No, the coin still has heads, tails, right? So those are two separate things. They don't change each other. So P, probability of A and B. What we're going to do is we're going to take the probability of A and we multiply that by the probability of B. So we just take the probabilities of each one and we multiply. All right, so independent means on their own, they don't affect each other. What does it mean to be dependent?
So they affect each other.
Do you want me to have an extra charger that I could use? It's okay.
Yeah, over there.
Okay, thank you.
Yeah, that they do affect each other. So if you're dependent on someone, that means that you need them in order to do whatever it is that you are doing. So, for example, on taxes are due in April here. Okay, if you have a parent, sometimes a parent can classify you guys as their dependent, meaning that you are depending on them to feed you, to get you clothes, things like that. And then they get a tax write-off for that. So dependent, in this case, means that the first event changes the outcome of the second event. Okay, so as you're going throughout your day, your events are changing. This happened when we were talking about our tree diagrams. If we go back to the tree diagrams, way back when. Okay, if I picked a pencil, I had different options than if I picked a pen. So my probability changes as I continue to pick more and more. If I pick a pen, I get blue, black, red. I have 3 options, but if I pick pencil, there's only 2 options. So the amount of options depends on what I picked, pen or pencil. Okay, to find that probability, we do probability of A. We're still going to multiply, but this time we're going to do probability of B after A happens. So in this probability of B after A happens, that's where we're showing that something changed. Okay, stop taking pictures of yourself. Do this. Okay, do this. Okay, so that probability is going to change as we go. So 2 things that we're doing as we work through this today. First thing we need to do is identify if this is independent events or dependent events. Do our events change each other or do they not change each other? Then we do need to find the probability itself. Okay, so this one says we roll a dice and we pick a card. I want a probability that I roll an odd number and draw not a heart. Okay, probability of rolling an odd and then not a heart. So first we need to decide, is this independent or dependent? If I roll a dice, is that going to change which cards are in the deck? Keon, put away your phone. No, it doesn't change. The deck doesn't change. It's still 52 cards. So it does not change. Is that independent or dependent?
Independent.
Independent. Good. So this is independent. They're 2 separate things. That can be another way to kind of think of things, is that they're separate. They don't interfere with each other. Okay, probability of an odd number. So now we're going to find the probability of each of these. We'll start with the odd. So on a dice, what numbers are on a dice? 6. 1, 2, 3, 4, 5, 6. And odd. Odd means that we're skip counting starting at 1. So we start at 1. What else is odd? 3 and 5. So how many are odd numbers? 3 out of 6. I can simplify that if I want to. 3 out of 6, 1/2. Okay, so that's my probability of my first thing, that I get an odd. Now I need to combine that with drawing not a heart. So probability, and then in parentheses I'm going to write that word not, heart. Couple ways to think about this here. We can look over here at our cards. Remember, heart is a shape. What's another way that we can call shapes in cards? Starts with an S.
Spades.
Right, spades is another shape. What do we call the shapes though? Suits. Okay, so there's spades, hearts, what else? Diamonds, and then this one is called clubs. Good. Because some people call this clovers. That's fine, call it clovers, but we do want to call it clubs. Yeah. Phone, away. No, away. Put it in your, no, not in your bed, no. Away. There you go. All right, clubs. So we have diamonds, spades, hearts, and clubs. We want not the hearts. So if I take away anything that's a heart, how many would I be left over with? How many are there in each suit? $13, yeah. So 13, 13, and 13. How many would that be together? 13 plus 13 is 26 plus 13, 39. So there's 39 cards that are not hearts out of how many cards total? 52. But we could also simplify that. And this might be another way that some people found this probability without having to do all the counting. 39 out of 52 is 3 out of 4. How many shapes are there that aren't hearts? How many shapes total are there? No, shapes, suits. 4, there's diamonds, clubs, spades, hearts, and how many of them are not hearts? 3 out of 4. So that would be another way to do that, or you could just simplify it. All right, so for our answer here, when we do this, we're going to take our probabilities. So we have our probability of our odd times our probability of our not hearts. So I'm going to take my odd, my 1/2, times my not heart, which is 3/4. Now you can use a calculator to do this. When you multiply fractions, it's pretty straightforward. You multiply straight across. So 1 times 3 is 3. 2 times 4, 8. So 3/8. Okay, let's make that into our decimal and a percent. So 3 divided by 8 is 0.375. And then as a percent, we would do times 100, and we get 37.5%. So is this likely, unlikely, even chance, certain, impossible? Good. What makes it unlikely? Good. It's in between 0 and 50. It's less than 50%, but it's not 0. All right, here we go with the next one, number 2. First, we're going to read the problem, decode it. It says, you draw one card from a deck and set it aside. You then draw another card. What is the probability that the first card is a queen and the second card is a 7? So let's imagine this. We take a deck of cards, we pick a card, and we set it aside. It's no longer in the deck. Then we pick another card. Is that deck of cards changing as we take cards out?
No.
Can you pick the same card twice?
Yeah. No.
No, not if I set it aside. This set it aside here is our really big key part. Okay, when I set something aside, that means it's no longer a part of what we had. So if you want to grab a highlighter, you can, or if you want to grab a colored pencil. I don't have a highlighter apparently, so I'm going to use colored pencil. This set it aside is what's really important. Because we set it aside, it's no longer there. It's not part of the deck anymore. And that makes it dependent. So it's going to change as we go, and you might be like, what the heck is she talking about? The cards don't change. We'll talk about it as we do this. Okay? Draw one card from a deck and set it aside. You then draw another card. Okay, first thing we need to do is find the probability that the first card is a queen. So I'm going to do my probability of a queen, or probability of Q. So how many Qs are there in a deck of cards?
4.
Good, 4. There's 4 of each of those numbers. So 4 out of 52. If you wanted to simplify that, you could. I'm just going to leave it as 4 out of 52 because I'm not going to do more work until we have to. Kevin, put your phone away, please. Thank you. Okay, but now for probability of 7. I took a queen out. Okay, I have a queen laying here. It's no longer part of the deck. How many 7s are there part of the deck? Did I remove any of the 7s? No, there's still 4 7s. But I took a card out of the deck. I took out a queen. So there's no longer 52 cards. How many cards are there in the deck? 51. I took a card out. I took out that queen. So that's what makes it dependent. And that's where I'm going to, again, use that highlighter, or if you use a colored pencil, highlight that 51 changes. That's how it's changing, is that we took a card out, so we don't have the same amount that we had before. Okay, then we just take our amounts and we multiply them. So I'm going to do my probability of a queen, which is 4 out of 52, times my probability of a 7, which I still have 4 7s, but I took a queen out. So instead of 52 cards, there's now 51 cards. Okay, and I can do the top. 4 times 4 is 16, but I don't know 52 times 51, so I'm going to use my calculator. When I use my calculator, 4 out of 52 times 4 out of 51. Okay, now we said 4 times 4 was 16, but this is saying it's 4 out of 663. Where did they get this 4 from? Good, they simplified it already. The calculator simplifies it before it gives it to you as an answer. So 4 out of 663, which then as a decimal is 0.006. Which times 100, if we need to, is actually 0.6%. So less than 1% chance. So when you think about things changing, it's really, does the circumstance change as we go, or is the circumstances staying the same? Did we reset in between? If things are reset or things are separate, that would be independent. If things are not resetting, there's a beginning and then there's something that happens as we go, there's a story to it, then it would be dependent. All right, so here we have PBS is giving out prizes for good attendance. Usually we do that in the spring. I don't know if we've done it. We did it for the No Phone February. A prize box has 4 pop sockets, 2 AirPods, and 3 free parking permits. 3 prizes are randomly drawn from the box and handed out. Find the probability of drawing a pop socket, a parking permit, and then a pop socket. So first thing we need to decide, is this independent or dependent? Dependent. Why is it dependent? Good, it's changing. What was our key word when we read through this that tells us it's changing? Good. When we say 3 prizes are randomly drawn from the box and handed out, they're no longer available. Once we give away a prize, it's no longer there. So it's dependent. Okay, first I need to figure out my total amount of things. So 4 plus 2 plus 3. 9. So there's 9 things to start. So first I need to do my probability of a pop socket. I'm just going to write pop. I know it's not the same as pop, but pop socket. So how many pop sockets are there in the prize box? There's 4 pop sockets out of 9. Now I'm going to multiply that probability of a parking permit, which I think, do you still have to get parking permits when you're here? Do we get rid of those now? That was from last year that I didn't change it. All right, so now I want parking permits. Okay, as I look at my parking permits, did I take any parking permits out? Nope, I gave away a pop socket, so I still have all the parking permits. How many parking permits are there? 3. But I did take out a pop socket. So how many things are there now in the bin? 8. I gave one of those pop sockets away. There's only 8 things now. Okay, now I have probability of another pop socket. I started with 4 pop sockets, but in this order, we gave away a pop socket, we gave away a parking permit. I started with 4 pop sockets. How many pop sockets do I have now? 3. Because one of those pop sockets was given away. From the overall bin, we had 9 things total. I gave away 2 things. How many things are left? 7. So we're finding the probability of drawing a pop socket, parking permit, and a pop socket. Because we're handing those things out, it's not refilling in between, it's not resetting, it's dependent. All right, again, you could multiply this by hand. I wouldn't recommend it personally because that just sounds awful to me, but you do you, bro. All right, so 4 9ths times 3 eighths times 3 7ths, we get 1 out of 14. Which is 0.071. That 4 tells us to stay at 1. Which then times 100 would be 7.1%. All right, we have one more to do. This one, be careful, you do need a little extra space than probably what I gave you on the paper. So if you have extra room, otherwise write really, really, really small. right, at golf practice, Naima has a bucket of golf balls. Golf is a spring sport. Any of you joining a spring sport? Baseball, track, softball? No? None of you? Track? Anyone? Okay, golf is a really good sport. You should join it. It's going to start soon. You're going to spend time outside. I mean, today you probably don't want to spend time outside because it's going to snow. But it's a really good time. All right, if you're not thinking about joining a spring sport, you should. It's a really nice time to be outside. So baseball, softball, track, infield. It's boys tennis, I think is now. Boys tennis. And there's trap shooting. I don't know, a bunch of stuff. Golf. All right. At golf practice, Naima has a bucket of golf balls. 7 yellow, 10 pink, 9 orange. Ayan picks one randomly to play each hole. Then puts it back in her bucket and chooses another. What is the probability that she will use only pink balls for 5 holes? So first thing we need to decide before we can find the probabilities is this independent or dependent? Can't, dude. There's a reason we put it in the bag. Come on, man. All right. We need to decide if this is changing as we go or if the bucket is not changing, the bucket of balls. Is the bucket of balls, as we play games, changing or not changing?
No.
She puts it back. So because she puts it back, does that make it changing or not changing? Not changing. So I'm going to switch colors here, and I'm going to highlight that puts it back. Puts it back is our key word there that tells us that it is going to be independent. It is not changing. Because she puts that ball back every time, it doesn't change. Haley, we got one more problem. Can focus for just a little bit. He does not have anything to drink right now. I see no water bottle on Nick. All right, we're looking for pink golf balls. So how many pink golf balls do we have? We have 10 pink golf balls out of, we need our total. So 7 plus 10 plus 9. 26. So 10 out of 26. She plays hole 1. Naima puts that pink golf ball back, grabs another one. How many pink golf balls are there now in the bucket when she puts it back? There's still 10. Remember, she puts it back. Out of 26. And how many times are we doing this? We're doing it for 5 holes. So we're doing it 5 times. 1, 2, 3, 4, 5. In my calculator, if I don't want to write the same thing out 5 times, how can I write it differently or quicker? What symbol tells me repeated multiplication?
Small square.
Yeah, but instead of squared, we're doing it to what power?
5.
Yep, 5. That little exponent. All right, we do it to the 5th. We get this crazy long fraction. 3, 1, 2, 5. Out of 3, 7, 1, 2, 9, 3. Crazy numbers. All right, even though there's the majority of the golf balls are pink in the bucket, I would think grabbing a pink golf ball 5 times in a row would be pretty common because there's 10 pink golf balls compared to the other ones. But when we look at this, it ends up being 0.008. We're always going to round to the nearest hundredth, 3 decimal places. And 0.008 times 100 is 0.8% chance. It's less than a 1% chance that for 5 holes in a row, Naima grabs a pink golf ball at random. Now, when you're playing golf, or when you're playing any sport, are you going to just randomly choose your golf ball? No, you might have like a lucky golf ball, okay, or a lucky puck, one that you want that's been well for you. All right, that's it for our notes today. Sorry if I was a little scatterbrained.